In section 24.3, we're going to look at some concepts in probability. Consider the possibilities associated with an event such as a coin toss or a roll of a die. Events that have equal likelihood or which we can expect to occur with the same frequency are said to have equal probability of occurrence. When we look at the general definition of probability, we would have the probability of A being defined by the number of points in A divided by the number of points in our sample space S. For every A in S, the probability of that event occurring must lie somewhere between 0 and 1. It might be equal to 0 for an impossible event or exactly equal to 1 for a certain event. Although a philosopher might question whether any events are actually certain. We tend not to get consumed with such considerations. For the entire sample space, the probability of the sample space is said to be 1, and that would have considered all possible events, so they must sum up to 1. For mutually exclusive events A and B, when you look at the probability of A union B, there is no intersection, so the probability of A plus the probability of B gives you the union because there's no intersection, or the probability of the intersection is equal to 0, or the null set. For an event A and its complement, the probability of A is whatever it is, and the probability of the complement of A would be 1 minus the probability of A, because again, A is an event and the complement of it is everything else. So if you summed up the everything else, that's got to be equal to 1 minus the probability of A. Probability and event combinations can be considered when you look at how much is in the intersection. In general, the probability of A union B would be in general defined by the probability of A plus the probability of B minus the probability of A intersect B. And why you have to subtract the probability of A intersect B is because you wouldn't want to double count that area. If the two events are mutually exclusive, that is, the probability of the intersection is 0, then you can leave off that last part, and the probability of A union B is just probability of A plus the probability of B, because there is no intersection, so there's no risk of double counting it. Mutually exclusive events are sometimes called disjoint events. A sample space partition is a sequence of events A1, A2, A3, all the way up to AN that form a mutually exclusive set of events for which the union of them all is equal to the entire sample space. Such a sequence is often called a set of mutually exclusive, collectively exhaustive set of events. Identifying such a set is very useful for addressing numerical probabilities. Why is that useful? Because if you've considered all possible events, then all possible events must collectively have a probability of 1 when you add them up. Conditional probability may be a new idea for you. The way conditional probability is defined and read is something new for most students. The conditional probability of event A given B, or A conditional upon B, is described by this equation. Probability of A given B is equal to the probability of the intersection of A and B divided by the probability of B. The way I remember that shorthand notation on the left is the A given that B has occurred, and notice the vertical line and B following. That always suggests to me that the probability of B is in the denominator. So that's how I remember how conditional probability is calculated. Again, you'll have these equations when you take exam 2 and the final exam. I've embedded an example problem using conditional probability here. In this case, we're looking at two different events. One is looking at the average flow rate in a stream, and event A is defined by the average flow rate exceeding 27 cubic meters per minute, and event B is that in this area, on a particular day, the rainfall exceeds half an inch. Usually, high rainfall would be associated with large flow rates, but not every single day, not every single time, but clearly these would be related events. If we are given the probability of A is 0.07, the probability of B is 0.1, and the intersection is 0.05, we know that there's a healthy intersection between these events. When we draw this on a Venn diagram, we're actually able to determine how much of each space is defined by within each slice, what the probability is in each slice. How did I get the 0.02 for that slice of A that's outside of B? Well, I know that the probability of A is 0.07, so if the intersection is 0.05, that slice has to be 0.02. Similarly, for the slice of B that's outside A. If I look at these three different numbers together and consider the only other possibility is that neither A nor B occurs, you can easily calculate, using the logic of the Venn diagram, what that probability is. It's 1 minus the sum of those three numbers. But in mathematical formulation, if I wanted to calculate that probability, I'd be using this expression where it's 1 minus the probability of A union B. And when I take the union, I have to remember not to double count, and that's why I have the minus probability A intersection B inside the parentheses. And I do get the result that I expressed, 0.88, for the probability that I'm not in either of the circles. Now let's look at some specific questions from this. Now that we have the Venn diagram completed, we can ask some specific questions for these cases. What is the probability that rainfall on a randomly chosen day will exceed half an inch, given that the stream flow rate exceeds 27 cubic meters per minute? In this application, let's use a strict application of the definition of conditional probability. What is that saying? It's saying that what's the probability of event B occurring, that is rainfall greater than a half inch, given that we can see that the stream flow rate exceeds 27 cubic meters per minute. It's the probability of the intersection divided by the probability of A. We know those now, so it's just a matter of putting those into the formula, and the intersection we found was 0.05. We were given that the probability of A is 0.07, so we just take this, divide those out, and we get 0.71 is the probability of B given A. Next, we want to find out what is the probability that the average stream flow rate exceeds 27 cubic meters per minute, given that the average rainfall does not exceed half inch. So what's this saying is, what's the probability of A given that we're in the complement of B, or what is the probability of A given not B? Not B is written as either B complement or B prime or B with a line over it. There's a number of different ways that people refer to not the complement of an event. So this is probability of A given not B. To get that, we need the probability of A intersect not B divided by the probability of not B. To get that, we would we'd have to find the probability of A intersect not B. That is, what is the probability that you're in A but not in B? We saw that. That was that slice, 0.02. And what's the probability of not B? It's that you're outside all the circles or in that little slice, and that probability is 0.9. Now that you have that, you can just take 0.02 over 0.9, and you have the probability of A given not B is 0.022. Next, we're going to look at independence. Independent events are events that aren't related. Two events, A and B, are said to be independent if, and all three of these are equivalent, the probability of A given B is equal to the probability of A, or the probability of A given sorry, the probability of B given A is equal to the probability of B, and the probability of A intersect B is equal to the probability of A times the probability of B. One occurrence the of of the event does not affect the occurrence of the other. So you might look at two situations that are entirely unrelated and consider them events, independent events. How are these depicted on a Venn diagram? Suppose that we have two events A and B that have probability of A is 0.4 and probability is 0.2. Clearly, the circle, if we're going to represent it as a circle, A is a circle in a Venn diagram, the A circle is going to be much larger than the B circle by approximately, or if we were drawing it precisely, correctly, twice as big as the circle that we use to represent the B event. On a Venn diagram, if they're independent events, there is an overlap. That what I'd really like is that 40% of B is in A, and also that 20% of A is in B. So we really want to have the intersection corresponding to the probability that the two events occurred at the same time. What if you have mutually exclusive events on a Venn diagram? If we have two events A and B with probability of A is 0.4 and probability of B is 0.2, if those events are mutually exclusive events, then when we draw them on a Venn diagram, how do they look? They don't touch. So we have to make sure that those circles have no intersection. So instead of trying to get the intersection sized right in our Venn diagram, we make sure there is no intersection for mutually exclusive events. When you have the intersection of multiple independent events, or given a series of independent events A1, A2, A3, all the way to AN, the probability of the intersection of this series of events is given by the probability that A1 has occurred, intersect the inner 2 has occurred, intersect the AN has occurred, is given entirely by calculating the probability of A1 times the probability of A2 times the probability of AN. And that's only true for independent events. That doesn't always occur. An example of independent events are, suppose you have two coin tosses in a row. You wouldn't really expect one coin toss to affect the outcome of the other one, so you'd regard those as independent events. So if you want to know what's the probability that you'll get heads two times in a row, you'd know that the probability of getting a head in the first row is 0.5, and the probability of getting a head in the second toss is 0.5, so you would simply multiply those two. It's 0.5 times 0.5. The probability of getting, if you're going to make two coin tosses, the probability that you're going to get two heads in a row is 0.5 times 0.5, or 0.25. So that's an application of this particular equation. Another way of looking at some probability events uses event trees. In event tree, we have different branches that come from a single event. So we might have branches A1 and B1 that might be the outcomes from event 1. Following event 1, which might be a coin toss, or for example, there's an event 2, and off each branch might have additionally branches that follow. In this case, we have two events, and there are two branches coming off each event. So when we look at the total results, we can have A1 and A2 branch, or A1 and B2 branch, etc. So we have these four possible results. If we could calculate the probability of each of these four results, we know that those are the complete list of probabilities, so they must have to sum to 1. And one of the reasons that event trees are particularly helpful is for cases where you have conditional probabilities. Again, reviewing conditional probability, it would essentially be saying that what's the probability of the next outcome given that you find yourself on this branch. So cases that involve conditional probability often lend themselves very well to event trees. That's it for section 24.3.